Okay, so good morning, everyone. Can you see my screen?
Yes, sir.
Good. Perfect. So let's continue with the discussion about the Heaviside theorems. And last time we introduced the first Heaviside theorem. Now we have to introduce the second. So let's consider you have a polynomial that is expressed again as the ratio of two polynomials in the Laplace domain. Obviously, the problem, just to recall, is that we want to transform back a polynomial from the Laplace domain to the time domain. Let's consider the polynomial that we want to transform is the ratio of two polynomials, n over d in the Laplace domain. The zeros of the denominator obviously are called poles. Please keep this name in mind. So let's consider now a scenario number 2, described by the second Heaviside theorem. If the denominator d contains poles whose multiplicity is different from 1, which means repeated poles, the factor associated to this pole gives rise to this contribution when you calculate the inverse of this Laplace transform. Basically, this repeated pole will give a contribution that is the exponential of SKT, where SK is the repeated pole, and we will see an example immediately. T is obviously the time, because we are transforming back to the time domain. And then there is that very unpleasant, but just apparently unpleasant summation, which goes from 1 to q, where q is the multiplicity. So if you have a root that is repeated 3 times, q will be equal to 3. And we will see an example. Of the derivative of order q minus I of a function phi, which we will define soon, times that time expression, time at the exponent I minus 1 divided q minus I factorial times I minus 1 factorial, where the function phi is n over d prime and is defined exactly as we saw last time. I know what you are thinking about. In this way, I do not understand anything. Just let's consider an example and everything will be more clear. I think now you should be able to see the whiteboard. Is that right?
Yes, sir.
Yes.
Perfect. And let's consider this scenario. So now the polynomial f that we want to anti-transform is 3s plus 1/2 divided 3s plus 1 times 2s plus 1 square. Okay, step number 1. Step number 1 is always the same. Find the poles. So could you please tell me what are the poles?
-1.
Yes, but negative 1/2 is repeated 2 times. Do you agree with me? Because there is an exponent 2. Do you agree that the multiplicity of this root of this pole is 2?
Yes.
So in this case, q is equal to 2. Q related to this pole. Now, with this being said, let's find the anti-transform. So we have to consider the contributions given by the single poles one by one. Pole number 1 is minus 1/3. So is this pole real?
Yes.
Is this pole repeated?
No.
No. And so, how would you calculate the contribution corresponding to this pole? With the first Heaviside theorem, because this pole is real and not repeated. Q is equal to 1 for this pole. The multiplicity is equal to 1. And so we can apply, to calculate the contribution associated to this pole, the first Heaviside theorem. And so f of minus 1/3 will be the numerator calculated in minus 1/3 divided what? B first. So here, remember, the coefficient of S is not 1. So we have to collect S outside of the bracket and suppress this term and calculate this denominator in minus 1/3 times the exponential of minus t over 3. And basically, what we get is something like this. Make sense for everyone?
Yes.
This is exactly what we saw last time. So now let's have fun. We have the repeated poles, minus 1/2, minus 1/2. The multiplicity Q is equal to 2, because it is repeated 2 times. So, are these poles reals? Yes. They are reals and they are repeated. So, what can we apply the first Heaviside theorem?
No.
Which one would you apply now?
The second Heaviside.
The second one. So now it's time to apply the second one. So we have to calculate the contribution associated to the pole minus 1/2. So again, now unfortunately I cannot project the formula, but please make sure you have the slide that I showed you a few moments ago with you on your table, and let's apply basically that formula. Summation of I going from 1 to Q, which in this specific case, you know, the summation goes from 1 to what?
2.
To 2. Summation from 1 to 2 of what? Derivative of order 2 minus I of the function phi, calculated in minus 1/2. Sk is minus 1/2, obviously, in this case. Times what? Time at the exponent I minus 1 divided 2 minus I factorial, I minus 1 factorial. Make sense?
Yes.
Okay. This is exactly that very unpleasant formula applied to this situation.
Dr. Glacia,
Yes.
there's supposed to be a exponential term in that equation, like e to the.
Oh, yeah. Sorry. Yes, you are right. Obviously, exponential of minus t over 2. Thank you, highly. Make sense?
Yes.
Okay. Now let's make this a little bit more explicit. Let's consider this summation. I equal to 1. So basically we have the derivative of phi with respect to s calculated in minus 1/2 times what? Time at 1 minus 1, time at 0. And time at 0 is equal to 1. So this term is now equal to 1. Make sense?
Yes, sir.
Okay. Plus. Let's consider now I equal to 2. derivative of order 2 minus 2, so derivative of order 0 of phi with respect to s. But wait a moment, wait a moment, wait a moment. Derivative of order 0, what that means? Who is the derivative of order 0 of a function? Is the function itself. The derivative of order 0 is the function itself. And so, directly, phi. Make sense?
Yep.
So, phi calculated in -1/2, and we will figure out what phi is in a few moments, times this factor, time at 2 minus 1, which is time at 1 time, divided 2 minus 2 factorial, which is 0 factorial. So what is 0 factorial?
1.
1 times 2 minus 1 factorial. 1 factorial, which again is equal to 1, times the exponential of minus t over 2. Is that clear?
Yes.
Okay, now we have to figure out who is this phi, because otherwise we cannot understand what we are doing. Now, to calculate this phi, just look at the formula. You don't need to remember the formula in mind. I don't remember that formula in mind. Just make sure you have your slides. If we apply the formula that you can see on the slide, phi is the numerator 3s plus 1/2, and that does not change, divided what? We have basically we have to apply this formula. Now, in the situation we have, just look at the initial expression. Is the coefficient of this s here equal to 1?
No.
No. What is that coefficient?
We have a 3.
It's 2. Make sense? It's 2. Make sense for everyone?
Could you explain that a little bit more?
In the expression that we have, this is the original expression. So basically, to calculate phi, applying this formula, we have to get rid of this term. Make sense?
Yes.
So now, compare this and this. In our situation, is this coefficient of this s equal to 1 or equal to something else?
It's 2.
It's 2. It's 2. And so, basically, just don't forget to do something similar to what we did the last time. Just bring these 2 out of the parentheses, and this will become. Make sense?
Yes.
So this is now phi. Just compare these 2 and see that basically to get phi from this expression, you have to do something like this. You need just a little bit of practice. But make sense for everyone?
Yes.
Yes.
Okay. Now, let me erase. Unfortunately, here we really do not have space. So let me rewrite phi. Okay, so we have to calculate now the derivative of phi with respect to s, and then evaluate this derivative in -1/2. And then we have to evaluate the function phi in -1/2 in order to get the analytical expression of this contribution. So phi calculated in -1/2 is 1/2. Now, the derivative of phi with respect to s basically is the derivative of the numerator times the denominator minus the numerator, the derivative of the denominator, divided the denominator squared. And basically, this derivative must be evaluated in -1/2. And you get 3/2. You need just to replace -1/2 in this expression. So basically, the contribution associated to the pole -1/2 is the following: is 3/2 plus phi calculated in -1/2 times t directly. Everything multiplied by the exponential of -t/2. So now the overall function f, which is the entire transform that we were looking for, the function f non-capitalized, function of time, which is the entire transform of the original function f capitalized, is the contribution associated to the pole -1/3 plus the contribution associated to the repeated pole -1/2. And so is this expression. Now, if you don't believe, just transform with Laplace this expression, and you will get back the function f capitalized that we considered at the beginnings. Again, if you don't want to use this method, which I believe is very mechanical, is very easy once you practice a few times, you may use the partial fractioning method. It is really up to you. So, does this make sense for everyone? Just practice, and we will practice a lot in the classroom. Now, there is a scenario number 3, and that we want to consider. And I think you should be able to see my presentation now. Is that right?
Sure.
Okay. So, again, we have a polynomial in the Laplace domain, which is basically the ratio of two polynomials, n over d. The zeros of the denominator are called poles again. So there is a scenario missing. What if the denominator d exhibits basically, what if the denominator d exhibits complex poles? So far, we have seen just real poles showing up just one time, or real poles repeated with the multiplicity q. What if the poles are complex numbers, a plus minus ib? So the pole associated, the factor associated to these poles gives rise to the following contribution to the Laplace transform. A exponential of at divided b, where a is the real part of the pole and b is the imaginary part of the pole, times, the sum of two oscillating functions that you can clearly see there, where psi r and psi I are the real and the imaginary part, respectively, of the ratio n over q, calculated basically in correspondence of the complex pole, where n is the numerator, is the original numerator of the original polynomial in the Laplace domain, and the q basically is what you can see on top of the slide. And again, in this way, you don't understand anything. Let's consider an example to clarify the meaning of these formulas. And, now you can see my whiteboard.
Yes.
Yes.
Okay, now, before we dive into these calculations, I think, guys, now you should note something. So basically, I told you a while ago that that when we have complex solutions, complex poles, those poles have a physical meaning because they normally give rise to oscillating behaviors. Now, based on what I showed you a few seconds ago, can you understand why? Basically, if you see in the slide that I just showed you, you will see a sinus function and a cosinus function. And those are oscillating functions. Do you agree?
Yes, sir.
Okay, so let's translate this in a more understandable language. And let's consider that f this time is given by an expression like this. So poles, always the same. We have to find the poles. The first step is find the poles. So the first pole is -1/4 associated to this factor. Now we have to find the poles associated to this factor. Delta is 16 minus 28, which goes to -12. Delta negative. So we have complex poles. Square root of -12. How to express this? Basically, let's simplify it a little bit. -2 plus minus square root of 3 I, where I is the imaginary unit. Does this make sense for everyone?
Yes.
Okay, so we have complex poles. So as a general rule, just remember that this system will probably respond in an oscillating way, in an oscillating fashion to any disturbance, and we will see this very soon. So the poles are -1/4 and this complex number here. So we have to find the anti-transformed as the sum of a contribution associated to this pole plus a contribution associated to this pole as usual. Let's start with the pole -1/4. Is this pole real?
Yes.
Is this pole repeated?
No.
No. And so how should we find the solution associated to this pole?
Use the first theorem.
That's right. First, Heaviside theorem. So f associated to -1/4 will be the numerator calculated in -1/4 divided. So we have to suppress the contribution associated to the pole -1/4, but this coefficient here is 4, is not 1. So we have to bring that out of the parentheses, suppress the remaining term, and then keep everything else as is. This denominator has to be calculated in -1/2, and everything has to be multiplied by the exponential of minus t over 4. So if you just replace minus 1/4 here, you will get 1 over 97 exponential of minus t over 4. And this is the first contribution. Now, we have to calculate the contribution associated to the complex pole. And so we have to use the third Heaviside theorem at this time. So, first of all, we have to rearrange a little bit this expression based on what you can see on the slide. In the slide, we show this as the function n, the numerator, divided the function q times. So basically, we have to rewrite this expression in this way, which becomes the numerator that stays the same, divided what? 4s plus 1, and then a. Who is a? Please, guys, can you please tell me who is a?
1/4.
It'd be -1/2 or -2.
Basically, yes, is -2. The complex pole is a plus minus ib. So a is -2. Make sense?
Yes.
Okay. Plus b. So who is b?
Square root of 3.
B is the square root of 3, and so b squared is 3. And indeed, if you develop this, you get s squared plus 4s plus 4 plus 3, which is exactly the same original expression. Make sense for everyone?
Yes.
Okay. So, basically, the contribution associated to this complex pole, just look at the formula. Exponential of minus 2t divided the square root of 3. Exponential of at divided b. Can you recognize this?
Yes.
Times psi I, cosinus of radical 3 time, plus psi r, sinus of radical 3 t. The problem is that now we don't know this psi I and psi r. Okay. So look at the slide. Psi I and psi r are the imaginary part and the real part, respectively, of n over q calculated in correspondence of the complex pole. Okay, so n over q. Can you please, guys, tell me who is n over q?
That's 3s plus 1 over 4s plus 1.
That's right. And basically, we have to calculate this in correspondence of the pole. Now you say, yes, but the poles are 2, because, you know, complex numbers, complex solutions come always in couple. Each complex comes with its own conjugate. So we have to pick the pole with the positive imaginary part. So we have to calculate this in -2 plus square root of 3i. Okay? So we have just to replace this here. And basically, we get something like this. -6 plus 3 square root of 3i plus 1. And so let me directly simplify as minus 5 plus 3 square root of 3i divided the denominator calculated there. So minus 8 plus 4 square root of 3i plus 1. And let me simplify this directly as minus 7. And basically now psi r is the real part of this number. Psi I is the imaginary part of this number. But wait a moment. How can I pick the real part of this number and the imaginary part of this number? This is a complex number, but this is not written in the standard form. Alpha plus minus I beta is not written in the standard form. So I have to modify, I have to rewrite this equation in the standard form. To do so, if you remember what you did probably in the calculus class or probably even at the high school, you may just want to multiply numerator and denominator by the complex and the conjugate of the denominator. When you have a number like this, you can get an equivalent number by multiplying numerator and the denominator by the same quantity. Let's multiply numerator and denominator by the complex and the conjugate part of the denominator. Can you please, guys, tell me who is the complex conjugate of the denominator?
Minus 7 minus 4 root 3i.
That's right. Simply, let's multiply numerator and denominator by the same quantity. And let's see what we get. We get 35 plus 20 square root of 3i minus 21 square root of 3i minus 12 times 3 times I squared. So who is I squared?
-1.
-1. And so 36 plus 36. And let's do the same here. 49 plus 28 radical 3i minus 28 radical 3i minus 16 times 3 times I squared. And I squared is -1. So this is plus 48. Don't you note everything? Basically, these and these cancel out. And what you get is basically 71 minus square root of 3i divided 49 plus 48, which is 97. So basically we have now this quantity n over q calculated in correspondence of the complex pole expressed in the standard form. Make sense for everyone?
Yeah.
Okay. So now with this being said, who is psi r and who is psi I? So who is psi r? Is the real part of this number. Make sense?
Yes.
Yes.
Who is psi I? the imaginary part of this number, minus square root of 3 over 97. So basically, if you replace this into the expressions that we got before, and we sum all of the contribution, you get this expression. And you clearly get an oscillating function. Complex poles always give rise to oscillating functions, to oscillating behaviors. We will see this very soon. Makes sense for everyone? So again, let's consider you don't want to use this. You want to use the partial fractioning method. Okay, as you feel comfortable with. But be aware that the partial fractioning method is, is devastating. Is boring. You will have to deal with long calculations. I think this is much easier. Once you have practiced it a couple of times, it will become much faster. So it's really up to you. And also, please, guys, note that all that you have studied here comes up in this class. So here, kinetics comes up, transport comes up, calculus, algebra. In this class, everything comes up together. Not in case you have this class at your senior year. It's basically a summary of what you did previously. Well, now let's go ahead and let's consider other examples about the application of the Laplace method to solve chemical engineering problems. Because we don't have to forget that our scope is not this. Basically, these calculations is just a technique. Our scope is to solve chemical engineering problems. Let me go back to a problem that you already know. We have a perfectly mixed isothermal tank. You feed an incompressible liquid with a volumetric flow rate VI dot. And basically you withdraw something simply by punching a hole here on the bottom of the tank. We demonstrated, I think 1 week ago, couple of weeks ago, that the outlet flow rate based on the Bernoulli's equation is alpha square root of h, where h is the level. And basically, we saw that the model for this system, the mass balance, was nonlinear due to the presence of the square root of h. And we linearized it. And just to go back to your notes, this is the linearized model that we wrote for this system. H is the instantaneous level, A is the cross-section area, HO is the initial level, the initial steady state level into the tank. Do you remember this?
Yes.
Now, we want to basically, we stopped here. We didn't know how to move forward. Now we know how to solve the differential equations. So we have a linearized differential equation that we can solve with the Laplace method. And let's do this. So we will see this problem in 2 ways. First, is this equation, is this a linearized equation written in the deviation variable form now?
No, it's not.
No, it's not. So let's solve now without, using the deviated variables, and then we will solve the problem again with deviated variables. And we will see that basically we get exactly to the same result. And we will understand that starting from now on, we need to always use the linearized equation in the deviated variable. So, scenario number 1. Let's proceed without using deviated variable. So, we have to solve this differential equation. Let's transform with Laplace. So, the Laplace transform of a summation is the summation of the Laplace transforms. So, A times the transform of this derivative. By definition, SH capitalized. H is the level in the time domain, H non-capitalized. H capitalized is the level in the Laplace domain. Make sense?
Yes.
So, definition of Laplace transform of the derivative. So, we have to know this. Plus constant Laplace transform of H is equal to what? This is a number. And so, basically, is the constant divided S. Make sense? We have transformed the initial linearized differential equation from the time domain to the Laplace domain. And we got an algebraic equation. This is algebraic. And so now we have to solve for H capitalized. We have to solve for the level in the Laplace domain. Okay, so just retrieve H from this expression. And is something like this. I'm just reporting, I'm skipping, the intermediate steps, because otherwise here into the space we do a big mess. So, does this answer our question? Our question is to solve the differential equation. So we want to get H as a function of time. Do we have H as a function of time now?
No.
No, we have H in the Laplace domain, but we want to anti-transform. So we are interested in H in the time domain. So we have to anti-transform this. So obviously in this way, the expression looks very complicated. So let's replace a few numbers and let's make this a little bit more manageable. So let's consider A equal to 5 square meters, HO 4 meters, VI dot 5 square meters per hour, and let's consider alpha equal to 1/2. And basically this expression becomes something like this. Much simpler, much more manageable. So, is this something that we can easily anti-transform, or do we have to resort to the Heaviside theorems? I think this is something that we can manage very easily without resorting to Heaviside. It is sufficient to break this expression as we did last time. Do you agree with me?
Yes.
Okay. So now, if you look very carefully, you will note, please have your table with you. Please open your table, the table of the Laplace transforms. You will note that this expression here resembles very closely something like 1 over S plus A. Do we know the anti-transform of this based on your table?
Yes, it's e to the negative at.
And if you look to this resembles closely another expression that you have in your table, for which you can immediately get the anti-transformed. And so here, what we need to do is just to make eventually this coefficient equal to 1. And basically, I can rewrite this in this way. Makes sense for everyone?
Yes.
To make this equal to this, I need this coefficient to be equal to 1, not 1/2. Make sense? So what I want to do is the following. Make sense? I'm just manipulating this to let this be equal to the standard expression, and this to make this expression equal to the standard one. Let me simplify as much as we can. And 80 divided 20 is equal to 4. So now I can really anti-transform immediately. Anti-transform of this term plus anti-transform of this term. So we get 4 exponential of minus t over 40 plus 36 1 minus exponential of minus t over 40. Make sense?
Yes.
Which means, if I simplify, means something like this. So, time in the x-axis, age level in the y-axis. If the time is 0, so at the time 0, how much the level is?
4.
4, which is exactly the initial value that we mentioned before. When t goes to 0, this exponential goes to 1. 36 minus 32 is 4. What if we consider long time? When time goes to infinity, where this goes? Where the
0. 0.
And so the asymptotic level is,
36.
36. Don't be shy, guys. So basically the level will change in this way, will go up. What if we solve the same problem with different numbers? For example, if alpha is equal to 4, all the other parameters being the same, from a physical point of view, this means that we are withdrawing much more liquid from them. So with alpha equal to 4 and all the other parameters equal to the values that we showed before, H will be in the Laplace domain something like this. The expression is similar to the one we got before, but the numbers are different. If you transform back to the time domain, H in the time domain will be 1 plus 3 exponential of minus t over 5. So, when time is equal to 0, what is the H?
4.
4. Again, exactly the initial value. What if time goes to infinity? What is the asymptotic level?
1.
1. So now the situation is like this. Makes sense? Yes, it does. Because now with alpha equal to 4, before alpha was 1/2, we are withdrawing much more liquid. And so this time, basically, the level will go down instead of going up. Make sense?
Yes.
Now, scenario number 2. So in this situation, we don't need to, resort to the EV side. We can entire transform in a relatively easy way. Let's consider now that let's have now the problem written in the deviation variable form. Let's consider the problem linearized and written in the deviation variable form, which we did last time. So just look at your notes. Now, the linearized model in the deviation variable is a dh over dt, where h is the deviated variable. The deviated h is equal to h minus what?
H naught.
Sorry?
The original steady state height value.
Yes, h minus ho. So, this is what we got last time. So, who is vi dot deviated? Is vi dot minus
V0 or V dot 0.
I dot 0 is the actual inlet flow rate minus the initial steady state inlet flow rate. So now, obviously, if we have the system written in the deviated form, the initial condition is that h deviated at time 0 is equal to
0.
0. So the system now, the equation, the model looks a little bit different because it's written in the deviated form. This is perfectly equivalent to the previous situation, but is written in the deviated variable form. Let's now solve with Laplace. Make sense? So now, obviously, this term is equal to 0. And basically, we have to solve for h capitalized in the Laplace domain. And this is what we get. So now we have to anti-transform this. So this looks similar to something that, to the expression that you have in your table. Just look at this. Can you recognize an expression that is there in your tables? Yes or not?
Yes.
Basically, we don't need to resort to EV side. This can be still anti-transformed using the tables. The sole problem is that we have to manipulate a little bit vi dot deviated. Vi dot deviated is vi dot minus vi dot initial at the original steady state. So in this expression, this deviated volumetric flow rate appears. And to have the numerical value of this deviated flow rate, I need to know the initial steady state flow rate, not just the actual, but also the original one. And I can get vi dot initial, vio dot from the original model at steady state. So when the system was originally at steady state, these equations, this mass balance equation, hold true. But at steady state, this term, this derivative, is clearly equal to 0. And so vio dot is alpha, the square root of ho, obviously. Does this make sense?
Yes.
Are you sure? Everyone? Okay. So in this expression, simply vi dot deviated will be vi dot minus alpha square root of ho. I just replaced this value with the value that we just found. And basically, this is the final expression for the deviated h. Now, just, and we can see this next time, just report here, replace here the same numbers for alpha, ho, vi dot that we used last time, and you will get exactly the same result as before. Obviously, this is h minus ho. And so, if you replace the numbers that we used before, you will get exactly the same value of h that we got last time. Does this make sense for everyone?
Yes.
So, you can proceed with the deviated variable or without a deviated variable in PreCycle. But we will see soon, next time, that we have to use always deviated variable. And you will understand the reason next time. Next time, before going ahead, I will take a few minutes to replace the numbers here and show you that this formulation with the deviated variables is equivalent to the previous formulations with the absolute variables. So if there is no question, have a nice weekend, and I will talk to you next Tuesday. If you need to talk for office hours, if you need any clarification, just send me an email. Just let me know, and I can talk with you possibly in a few minutes or in a few hours. Have a nice weekend.
Thank you.
Thank you.
Bye.